So in this lecture video, we're going to talk about section 6.3, which talks about the graphs of the tangent, cotangent, secant, and cosecant function. So first off, our amplitude is going to be given to us by the absolute value of A, and our phase shift is going to be given by negative C divided by B. And again, where are these A's, B's, and C's coming from? If you imagine that our trig function is of the form of A times, and then here you can insert any trig function that you want. In the previous sections we were talking about sine and cosine, but here obviously we're expanding that a little bit. So here I'll just write a trig function. You can substitute in here any trig function that you want. That trig function then we're going to take of B times x plus or minus c, and then all of this is then going to be plus or minus d at the end. So what we were seeing before in the previous section was this was like a times sine of bx plus or minus c, and then at the end we're going to add or subtract d from it. So like I just said, in the previous sections this might have been like a times the sine of bx plus or minus c, and then plus or minus d at the end. But here now I just said any trig function. Like I said, we can either use sine and cosine like we were doing before, but now we're going to expand that to the tangent, the cotangent, the secant, and the cosecant. So that's where these a's, b's, and c's are coming from. Here we have the graph and also some properties of these different trig functions that we've been looking at. This first one right here, and some of this might be a little bit hard to see on the video, but a little bit more clear in the notes that you have. Here is going to be the function of sine. So this is the sine function. Like we already know, for sine, the domain is going to be all real numbers, and then our range is going to go from -1 up to +1. So the sine function is going to live within that range as long as it's just y is equal to sine of x. So we don't have any of these other shifts that we have up here. And then the period is going to be from 0 to 2 pi. You can see in here we have an entire cycle of the sine function, and then obviously it just keeps on going on and on and on, and it repeats itself every 2 pi. So here I just took the example of it going from 0 to 2 pi. Obviously we could start the cycle for this going from pi then to 3 pi, but it's going to repeat itself every 2 pi. We've also seen the cosine before. The cosine is simply just a little bit shifted from the sine, but again the domain is all real numbers, and the range again goes from -1 to 1, and again we have a period of 2 pi. What we haven't really taken a closer look at, though, is these remaining 4 trig functions, at least in the previous sections. Here, this is the tangent trig function. The domain is going to be all x values such that x is not equal to this stuff right here. And this might be a little bit hard to see on the video, but we're going to revisit it again down here at the bottom in this definitions box that's coming up here in just a minute. So I'm not going to go into this stuff a whole lot up here in these pictures, but keep in mind that this graph right here is the tangent. And what's important that's different from the sine and the cosine is that the tangent now has these vertical asymptotes. These vertical asymptotes are going to be really important when we look at what's called the principal cycle later on. But keep in mind that the sine and cosine don't have vertical asymptotes, but the tangent does. And so does the cosecant. So here, this graph down here is of the cosecant. This one is of the secant. So here, just to make sure that we're all on the same page, this spot right here, this is pi. This spot right here, this says 2 pi. Here then, this spot right here says pi over 2, which means then that this spot right here is going to be 3 pi over 2. Just to help you get a little bit of the bearings here in case you can't see that. This spot right here is obviously the origin. And then here, this is the secant function. This spot right here, this is pi. This one right here, this is 2 pi. And then this right here is our origin. But as you can see here in the secant function, we again have vertical asymptotes. And lastly, the cotangent function. This spot right here, this is pi. This spot right here, this is 2 pi. And again, for the cotangent function, we again have vertical asymptotes. So let's go down here to our definitions box. This is right here highlights not just the stuff that was a little bit hard to read up here in these different graphs, but it also gives us a little bit of additional information. First off, we have these 6 trig functions so far, and for 4 of them, for the sine, the cosine, the cosecant, and the secant, the period of these 4 trig functions is 2 pi divided by the absolute value of b. However, for the tangent and for the cotangent, the period is pi divided by the absolute value of b. So instead of it being 2 pi, it's just pi. So make sure that you're catching that difference right there. Now here we have something that's called the principal cycle. And what's important for the principal cycle is that the principal cycle happens in between our vertical asymptotes. So let's take a look at this again. Let's start off with the first one, the secant. Again, here's our graph of the secant. And here we have a vertical asymptote. And here we have a vertical asymptote. And in between these 2 vertical asymptotes, this portion of our graph right here, this is what we're going to call our principal cycle. So like I said before, if this right here is pi, and here we have our origin, then one of our vertical asymptotes is at 1/2 of pi, or pi divided by 2. And then this vertical asymptote over here is going to be at negative pi divided by 2. And as you can see right here, our principal cycle goes from negative pi divided by 2 to pi divided by 2. Now, another portion that's really, really important about it is that in between negative pi divided by 2 and pi divided by 2, we have bx plus or minus c. So bx plus or minus c, which again, if I try to come up here real quick, that's what we're taking the trig function of. So whatever we're taking the trig function of, we have to put that in between here. And now what we can do is we can, if the question asks us to, we can solve for x. But keep in mind that for the secant, we're always going to have to the left and to the right of these inequality signs, negative pi divided by 2 and pi divided by 2, because that's where our vertical asymptotes are for the secant. Same thing happens for the tangent. Again, in between here, we're going to have bx plus or minus c. And for the tangent, now again, for, over up here is the tangent. I was looking at the cotangent. Up over here for the tangent, we again have a vertical asymptote right here. And again, if this spot right here is pi, then this vertical asymptote is pi divided by 2. And over here, we're going to have negative pi divided by 2. So that this, in between here, this is what we're going to call our principal cycle. So just like we had before, we have negative pi divided by 2 and pi divided by 2. But let's take a look now at the cosecant. So the cosecant is this graph up in here. Now, here we have it a little bit different. Here, we're going to look at this vertical asymptote, and we're also going to look at the vertical asymptote that is essentially the y-axis. And we're going to say in between these two, this is where we're going to have our principal cycle, so that our principal cycle is going between 0, and if this is pi divided by 2 right here, it's going to go between 0 and pi. So again, if you look down here for the secant, the principal cycle is going to go between 0 and pi. Lastly, We'll also take a quick look at the cotangent. The cotangent, we're going to again go between our vertical asymptotes, and that's the really crucial part about this, is we're going in between our vertical asymptotes. And in between these vertical asymptotes right here, this one is what we're going to consider to be our principal cycle. And therefore our principal cycle is between 0 and pi. So down here, if we take a look at the cotangent, the principal cycle is going to be between 0 and pi. And again, for all of these, we're putting in between those inequalities bx plus or minus c. Now, I kept stressing for the principal cycle is in between our vertical asymptotes. And again, if we look at these graphs for these 6 trig functions, we can see that the tangent, the cotangent, the secant, and the cosecant all have vertical asymptotes, and therefore they all have principal cycles. However, the sine and the cosine function do not have vertical asymptotes, and therefore they also do not have principal cycles. So one of the things that I'm hoping that sticks with you is that principal cycles happen in between vertical asymptotes. Alright, let's just take a look at the odd and even functions. So first off, the even functions are cosine and the secant. Now, let's try to jog our memories again about what it means to be an even function. An even function, first off, we're going to be symmetric about the y-axis. And for odd functions, we're going to be symmetric about the origin. Algebraically speaking now, so I'll make these lines right here. Algebraically speaking, in order for us to have an even function, if we plug in a negative value into this even function, we're going to get the exact same result as if we would just plug in a positive value into the even function. However, if we have an odd function and we plug in a negative value, that's the same thing as bring the negative value outside and just plugging in a positive value. Again, a really simple example of an odd function would be if f of x is equal to x cubed. That's what I've been giving in the last couple of sections. And for an even function, a really easy even function would simply just be x squared. So here, if we plug in a negative value into x squared, it's the same thing as plugging a positive value into x squared. The result is the same. However, if we plug a negative value into x cubed, it's the same thing as plugging in a positive value into x cubed, as long as we take the negative of it after we plug in the positive value. Alright, we're going to be using the characteristics of even and odd functions later on in examples in that section. And what you should really be paying attention to is we're going to start wanting that this b right here, or more specifically, this b right here, we want to start dealing with the fact that this b is positive. So if we ever have this b being a negative value, depending on whether or not we're using an even function or an odd function, we want to manipulate that somehow so that this b then becomes positive. So another way of saying that is this. If this b is negative, and we're dealing with an even function, so either the cosine or the secant, we can simply just turn that b into a positive, because we know that plugging in a negative number is the same thing as plugging in a positive value into an even function. However, on the other hand, if this b is negative, and we're now dealing with an odd function, we can still make that b positive, but then we have to make sure that we're multiplying the entire function by a negative number as well. So again, once we're dealing with principal cycles, one thing to keep in mind is that we want to have this b value be positive whenever we're dealing with the principal cycle. But once we get to an example like that, I'll make sure that I start pointing it out. Lastly, for the domain and range, you can see the domain and range from these graphs up here. If you look at the domain for the secant, and again, here's the graph of the secant, we can plug in any x values that we want, except for when we have these vertical asymptotes. Now, the reason why we can't include these vertical asymptotes in our domain is, well, for one, they're vertical asymptotes, but the secant is also defined as 1 over cosine of x. And what these vertical asymptotes are doing is whenever our cosine function is equal to 0. Remember that there's certain spots where our cosine function can be equal to 0. And whenever our cosine function is equal to 0, if the secant is 1 divided by the cosine, now that would just be the same thing as saying 1 divided by 0, and we know that we can't divide by 0. So that's what's happening with these vertical asymptotes. So therefore, the domain for the secant is just going to be all x values except for whenever we have vertical asymptotes. And that's going to be true for every single one of these trig functions that have vertical asymptotes. Right? If you recall from a previous section that the domain for both the sine and the cosine function is simply just all x values, but here we're going to have to pay attention to whenever we have vertical asymptotes. And that's what this notation down here says. It says for the secant, our domain is simply just going to be all x values except when we take an asymptote and we have plus 1/2 of the period and any multiple of that period. And here for the tangent, again, it's going to be all x values except for any asymptote plus the period times some integer value. Right here, k represents some integer value. And the same thing holds true for the cosecant and for the cotangent. The range for these is, as we can see right here, for the tangent and for the cotangent, the tangent goes from, right, we can go all the way down to negative infinity and go all the way up to positive infinity. So for the same thing holds true for the cotangent. We can go all the way up to positive infinity on the y and down to negative infinity on the y. So therefore, for both the tangent and the cotangent, our range is from negative infinity to positive infinity. But here, what we have for the cosecant and for the secant function is, you can see there's a range in here that we never touch, right? In between these two dotted lines right here for the cosecant, and I could draw similar ones right here for the secant. So what we're doing here is we're saying we're going to go from negative infinity, but then here we have a similar shift that we did in the previous section whenever we were looking at the range. So if all of that so far was clear as mud, don't worry about it. We're going to get into some examples where we're going to start to apply some of this stuff, which is on the next page of our notes. And the first one that we're going to deal with is tangent. So first off, tangent is defined as the sine of x divided by the cosine of x. And here it's as the tangent of x is undefined whenever we have vertical asymptotes when the cosine is equal to 0. So here, let's first try to remember what the graph of the cosine looks like. So this is a little bit hard to read right here, but this spot right here, this is pi, so therefore this right here is negative pi. And we're going to say that this dot up here, that this is equal to 1, and this one down here, this is equal to negative 1. So therefore, here we should have something that looks, oh goodness, like this, roughly speaking. And then we're going to continue to repeat this So let's see right here. I'm going to say that this is 3 pi divided by 2. It's going to come up here. Wow. Okay. Then this is going to be negative 3 pi over 2. So this looks something like that, right? So question then becomes is when does the cosine of x equal to 0? Well, had I drawn this a little bit nicer, we're going to see that the cosine of x is equal to 0 whenever we have, say, negative pi divided by 2 and pi divided by 2, right? This spot right here and this spot right here. But again, it's going to continue to repeat itself. So we're going to have a 0 value right here and a 0 value over here. So therefore, we're going to hit the 0 mark at every pi that we add either to this pi divided by 2 or subtract from it. So therefore, we can also say that this is going to be 0 at 3 pi over 2 or negative 3 pi over 2. And so on and so forth. We can come up with a whole bunch of different ones. So that's where we have these 0 values. But to be a little bit more specific about it then, is we have a formula that says this. That's why I skipped ahead here to this line. Technically speaking, where does cosine of x equal to 0? If we have 2n plus 1 divided by 2 times pi, where n is an integer. So 2n plus 1 divided by 2 times pi, where this n right here that we're plugging in, that's an integer. And remember, integers are negative 3, negative 2, negative 1, or you can have 5, 6, 7, 8. So you can think of them as whole numbers that are either negative, positive, or obviously also equal to 0. So therefore, any value that you plug in here for n, right, any integer value that you plug in here for n, that's going to tell you where we have the cosine being equal to 0. And whenever we have the cosine equal to 0, that's when down here in our denominator we would have equal to 0. So that's also why we're going to have vertical asymptotes for the tangent at these different spots. Alright, so let's move on to question number 1. So again, just to make sure that we're all still on the same page, and I wrote this on the previous page, but on this page we're dealing with a lot of tangent examples. So it's going to be a times the tangent of bx plus or minus c, and then here we're going to have plus or minus d at the end. So they're starting off as us in number 1 with just the tangent of x. So the principal cycle for the tangent of x is going to be, for this problem, is going to be from negative pi divided by 2 to pi divided by 2. If we want to graph this then, if this right here is pi divided by 2, and this right here is negative pi divided by 2, our principal cycle is going to be in here, so this right here is our principal cycle. The period for the tangent is given to us by p is equal to pi divided by the absolute value of b. Well, here the absolute value of b, or simply just b, is just 1. So therefore here we have that the period is equal to just pi. Right? We have no coefficient right here in front of x. So again, as always, we can just imagine that imaginary 1 right there, or that make-believe 1 if we don't want to call it an imaginary 1. So therefore our period is just equal to pi. So therefore, if this is pi divided by 2, here we're going to have, again, 3 pi divided by 2, and this tangent graph is going to repeat itself. Here we're going to have negative 3 pi divided by 2, and again, this tangent graph is going to repeat itself, and so on and so forth. The domain then is going to be all x values such that these x values are not equal to, again, what we had before, 2n plus 1 divided by 2 times pi. And that's where we have our vertical asymptotes. Again, here n is an integer. And for the range of tangent, as we can see, we're going to go all the way up to positive infinity, all the way down to negative infinity. So therefore, our range is going to be from negative infinity to positive infinity. Alright, let's move on to number 2. This would be a good spot for you to pause the video now and give it a chance by yourself. For number 2, we're still going to use this notation up here. So first off, what we can see is that start to determine what A is equal to, what B is equal to, what C is equal to, and what D is equal to. And that'll help us fill in some of these answers down here. Well, for A in this case is going to be equal to 2. B is whatever we're multiplying to x, so B is going to be equal to 4. C is whatever we're adding or subtracting to this x term inside the parentheses, and we're not adding or subtracting anything to that. And D is going to be what we're adding and subtracting to this entire term right here, and again, we're not adding or subtracting anything to that, so again, that's going to be equal to 0. Now, let me point out what I was saying before about the fact that we wanted to have B be positive. Here, this 4, we said that this was B. So, what I was saying before, let me make a little note over here, is that whenever we're looking at the principal cycle, we want B to be greater than 0. If B was not greater than 0, then again, for the tangent function was an odd function, so then we would have to bring that negative sign, say this was a negative 4, we would change it to a positive 4, but then bring that negative sign out front. But that's not something we have to worry about in this example because here B already is positive. Our principal cycle then is given to us by negative pi divided by 2 has to be strictly less than anything that's inside here inside the parentheses, and then that has to be strictly less than pi divided by 2. So again, let me pull up the definitions that we had before just to make sure that everybody's on the same page with what I'm doing. We're looking at the tangent right here. So here for the tangent, I'm taking negative pi divided by 2 and pi divided by 2, and in between it, I'm putting everything that's inside our parentheses of which we're taking that trig function. So here I took pi divided by 2, negative pi divided by 2, here's pi divided by 2. So in between here, I'm going to put everything that we're plugging into the trig function, which is simply just equal to 4x. Now what we're going to do is we're going to solve for the x. The only thing that we want to keep inside here is x. So therefore I have to divide this and this by 4. If I divide everything by 4, now in between those inequality signs I'm just left with x. And over here, negative pi divided by 2 divided by 4 is the same thing as negative pi divided by 8. And here, pi divided by 2 divided by 4 is the same thing as pi divided by 8. So therefore, our principal cycle is going to go from negative pi divided by 8 to pi divided by 8. Figuring out the principal cycle is definitely something that you should be very, 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 very familiar with. It's a very, very common type of question to ask on exams or final exams or quizzes or homework or stuff like that. Alright, let's go on to the period. The period for the tangent, again, while I'm at it, let me again bring this back up here. For the tangent, the period is given to us by pi divided by the absolute value of b. So that's what we also had up here. So it's P is equal to pi divided by the absolute value of B. Here we know that B is equal to 4, so it's the absolute value of 4, which is just the same thing as just 4. The domain for this, again, is going to be all x values such that x is not equal to, and now this is super important. This is something that a lot of people get wrong. But what we want to start off with here is we want to have our vertical asymptote, right? So here what we're doing is we're looking at the domain for our tangent. And the first thing that we want to look at is we want to start off with our asymptote. And then we're going to add plus the period times k. So we're doing this portion of it right now, the asymptote plus the period times k. So our asymptote here is pi divided by 8. We have an asymptote at pi divided by 8. And an easy way to do that is simply just to take the positive portion of where our principal cycle ends. Right, so here's pi divided by 8, which means that here at pi divided by 8 we have to have a vertical asymptote. So now here we have our vertical asymptote, and we're going to add to this the period. We just determined that the period was pi divided by 4, and pi divided by 4 times k. So let's take a look at exactly what this means, right? What we're saying is that the domain, you can include all x values, but, and I know that these numbers here are a little bit off, but our vertical asymptote, the positive vertical asymptote of our principal cycle, here in this example, happened to be pi divided by 8. So then what we're going to say is, well, we can't include, right, not equal to, we can't include pi divided by 8, or if we go one period above that, right, so here if you let k be equal to 1, then we're going to add pi divided by 4 to it. So then if you go one period above that, this right here is also going to be a vertical asymptote. If you go one period below it, we're also going to end up at a vertical asymptote. So that's why we're saying here that pi divided by 8 plus the period times k, where again k is an integer. Now, sometimes you'll see this written as k, sometimes you'll see this written as n. I think that your textbook uses n, but here in the notes they've been using k. Either way, we're just multiplying an integer to it. Lastly, and luckily, probably the easiest thing that we've done so far is the range. We can see that the range goes up to positive infinity and then goes down all the way to negative infinity. So we're going to go down to negative infinity and up to positive infinity. Alright, at this point I would highly recommend that if 1 and 2 weren't very clear yet, that you maybe go back and you take a look at those. If you're kind of getting the hang with this stuff so far, pause the video, give number 3 a chance by yourself, and then you can see whether or not you got the answers correct. Alright, so number 3 now we're dealing with this being our function. Again, for the principal cycle, what's extremely important is that b be greater than 0. Hope you can't see that here. For the principal cycle, what's really important is that b be strictly greater than 0. Well, just like we did before then, let's try to identify what a is, what b is, what c is, and what d is, and hopefully that'll help make our life a little bit easier here as we try to answer some of these questions. A is our leading coefficient, or just a coefficient that's out here. We don't have one, so we can imagine it as it just being equal to 1. B is what we're multiplying to our x, and here we have x divided by 3, so you can think of that as multiplying it by 1/3. C is whatever we're adding or subtracting from the x term, right? More specifically, it's what we're adding to the x term. So therefore here C is negative pi divided by 20. We want to make sure that if it's a negative that we include that negative, and if it's a positive that we make that a positive. So technically speaking, it's whatever is being added to this x term, because here we're like adding a negative number to it. And lastly, D is whatever we would add or subtract to all of this, and here we're not adding or subtracting anything to all of that, so we just have it as D is equal to 0. Now, luckily for our principal cycle, we said that we want to have B being strictly greater than 0. B is strictly greater than 0. So therefore, for our principal cycle for the tangent, we're going to have this as being negative pi divided by 2. And here we're going to have pi divided by 2. And in between here, we're going to put whatever we have inside these parentheses. So we have x divided by 3 minus pi divided by 20. Now, just like we did before, what we want to do is we want to solve for x. We only want to have x in between here. And we can go through a couple of different steps. Here, we would have to get the same denominators, and then we would have to add 20, pi divided by 20 to everything, and then we would multiply everything by 3. I think everybody should feel comfortable about how to solve for x. So therefore, this should get us to negative 27 pi divided by 20 is strictly less than x, which is strictly less than 33 pi divided by 20. So if you solve for x, you should end up with this, which means that our principal cycle is going to go from negative 27 pi divided by 20 to 33 pi divided by 20. Right, negative 27 pi divided by 20 to negative 33 pi divided by 20. Can't get the entire page on this, so let me try to zoom out here a little bit. Alright, that looks good. Alright, for the period, again, P is equal to pi divided by the absolute value of B. Here, the absolute value of B is just the absolute value of 1/3, which is just the same thing as 1/3. So therefore, here, this is going to be equal to 3 pi. So the period for this function is equal to 3 pi. The phase shift, so this is the first example that we have a phase shift. The phase shift is given to us by negative c divided by b. So we have negative c, so here negative, we said that c was a negative pi divided by 20, and b was equal to 1/3. So therefore we have negative pi divided by 20 divided by 1/3, or if you want to get rid of these two negatives and make it into a positive, and also multiply by the reciprocal, we'll get 3 pi divided by 20 for the phase shift. The domain, again, so here encroaching on the territory a little bit for the domain. The domain is going to be then all x values that are not equal to, we're going to again start with our vertical asymptote, our positive vertical asymptote from our principal cycle, which is 33 pi divided by 20. And we're going to add to it the period, which is 3 pi, times k, where k is an integer. So again, we're taking a vertical asymptote. Typically, the vertical asymptote that we take is the positive cutoff of our principal cycle. and then we add to it 3 times pi times k, and k is some integer value. Lastly, the range, and the range is going to be the easiest for all of these. We're always going to go from negative infinity to positive infinity. Alright, so that is the tangent. The next page in the notes that we're going to go to is the cotangent. And we're going to really do a lot of the same. So because this is going to start to be very, 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 very similar to what we did on the previous page, I'm going to try to speed it up here a little bit. So first things first. First thing that we want to look at is we want to look at the sign. The sign is going to go up to -1 and all the way down. Go all the way up to +1 and all the way down to -1. It's going to be 0 at the origin, it's going to be 0 at pi, and 0 at negative pi. And it's going to look something like this. And then we're going to keep repeating our cycles. So therefore, where does the sign of x equal to 0? Well, it's going to be 0 whenever x is 0, and then every pi or multiple of pi after that. So therefore, it's going to be n times pi, where n is an integer. And therefore, since the cotangent is defined as the cosine divided by sine, whenever the sine is equal to 0, that's where we're going to have our vertical asymptotes for the cotangent. So therefore, the cotangent is going to have vertical asymptotes both at 0, pi, 2 pi, and so on and so forth, but also then at negative pi, negative 2 pi, and we can keep going in the negative direction as well. The principal cycle for the cotangent, for number 4, since we literally just have the cotangent, is going to be from 0 to pi. The period for the cotangent is given to us again by pi divided by the absolute value of b. Here the absolute value of b is just 1, so therefore we just have pi. And the domain is going to be all x values such that these x values are not equal to where we have our vertical asymptotes, so therefore all the ones that are not just n times pi, again where n is an integer. The range for this, the range is going to be a little bit easier if we start to look at the graph of the cotangent. So the graph of the cotangent does this. We said that the principal cycle is between 0 and pi. So here we have between the y-axis and here we have pi, and it looks like this. And then we have this graph right here just repeating. So here this then went from pi to 2 pi. Here we're going to go from the y-axis down to negative pi, and so on and so forth. So as you can see from these graphs, we always go up to positive infinity and negative infinity, so our range therefore is going to go from negative infinity to positive infinity. Alright. Just like we did before, we have that our function now is a times the cotangent of bx plus or minus c plus or minus d. So just like we did for the last 2 examples on the previous page, we're also going to start off the same way for number 5 and number 6. we're going to try to identify what A is equal to, what B is equal to, what C is equal to, and what D is equal to. And then we're going to use that in order to find these things down here. Alright, so let's take a look. Here, A is going to be that coefficient, so A is going to be equal to 3. B is whatever we're multiplying to the x term, and what we're multiplying to it is 1/4. C is what we're adding and subtracting to this x term inside the parentheses. We're not adding and subtracting anything. And D is what we're adding and subtracting to this entire term, and again, we're not adding and subtracting anything. So therefore, if we're trying to find the principal cycle is we're going to go between 0 now and pi, and we're going to plug anything in between these two inequalities that we're trying to plug into our trig function. So we're going to have x divided by 4. Again, if you look in the definitions box on the first page of this section, you'll see that the principal cycle for the cotangent goes from 0 to pi with these two inequalities, and anything that we have right here, this is the bx plus or minus c term. Alright, so just like we did before now, we're going to solve for x. So we're going to multiply everything by 4. And if we multiply everything by 4, we get that it's 0 is strictly less than x, which is strictly less than 4 pi. Or our principal cycle is going to go from 0 to 4 pi. Our period is given to us by p is equal to pi divided by the absolute value of b. The absolute value of b is just the same thing as the absolute value of 1/4, which is just 1/4. So then therefore this is going to be pi divided by 1/4, which is just the same thing as 4 pi. So our period is also 4 pi. Now our domain is going to be all x values that are not equal to. We're going to start off with our vertical asymptote, and again, typically speaking, the vertical asymptote that's used is the positive cutoff for our principal cycle, and to this we're going to add our period. The period we determined was also 4 pi, and then this is going to be multiplied by k, again, where k is an integer. And lastly, we have the range, and the range is going to go from negative infinity to infinity. Alright, number 6. Again, this is a great spot for you to pause the video, give number 6 a chance by yourself. Just like we did in the previous problems, we're going to try to identify A, B, C, and D so that we can use these going forward. Here, A is equal to So here this is a great example. Here what we would say is that A is equal to 1. So I'm gonna write that down right here. Now B is whatever we're multiplying to our x term. What are we multiplying to our x term? We're multiplying negative 3 to it. Now, one of the things that I didn't remind you of for question number 4 and question number 5, but I did say it repeatedly on the previous page, is that for whenever we do the principal cycle, we want to have that b is strictly greater than 0. But we have a problem. Here, b is not strictly greater than 0. Here, b is negative. But we want b to be positive. So what can we do? Well, if you remember for the cotangent function, the cotangent function is an odd function. So what does that mean? That means then that we can make this inside the parentheses positive, but we have to bring out the negative sign out front. So this is the same thing as the negative cotangent of 3x. But since we brought out the negative sign out here, can't just pull out a negative out of this. We have to pull out a negative out of everything that's inside the parentheses. So then this is going to become minus pi divided by 5. So here, when I kept saying we want to have b be greater than 0, this is the first time that we're really running across it. Here b was less than 0, but since the cotangent is an odd function, we know that we can take the negative out of this and pull it out front. Right? So we pulled a negative 1 out of negative 3x, pulled a negative 1 out of pi divided by 5, so it became positive 3x and negative pi divided by 5, brought that negative sign out front. Now, what we want to look at is we want to use this function right here, right, which is identical because it's an odd function. But now if I ask you what is a equal to, now you would say that a is equal to negative 1. And what would b be equal to? Again, b is whatever we're multiplying to x, so b would now be a positive 3. So when I kept stressing before that b should be greater than 0, this is a prime example of what I meant for that. Here it's an odd function, so we can manipulate it. If it was an even function, we could have just made everything inside the parentheses positive, because an even function allows us to do that. Alright, now what is c equal to? C is what we're adding to or subtracting from the x term, and so now it's negative pi divided by 5. And d is whatever we're adding or subtracting to the entire thing, and that's still just equal to 0. So now we want to use this a, this b, this c, and the d as we answer these questions going forward. So now our principal cycle, again our principal cycle for the cotangent is going to go from 0 to pi. And now we want to put in between here the bx plus c term, which now is just 3x minus pi divided by 5. Right? It's the one that we changed up right here. This right here is really, 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 really important. After we get this set up, the next step is the same that we were doing before. We simply just solve for x. And if you solve for x, there's a little bit of arithmetic that goes along with it, common denominators and so on and so forth. But that should be something that's well within your wheelhouse now, and we would get the following answer. Alright, so then our principal cycle is going to go from pi divided by 15 to 2 pi divided by 5. Our period now is still given to us by pi divided by the absolute value of b. Here it's going to become pi divided by 3. And now our phase shift is given to us by negative c divided by b. And negative c is a negative pi divided by 5 divided by b, and b is equal to 3. So therefore this then comes out to be pi divided by 15. That's our phase shift. Our domain is again all x values that are not equal to. We're going to start off with, you can still start off with this upper one right here, which is our upper limit for the principal cycle as our vertical asymptote. And then we're going to add to it our period, and we said that the period was pi over 3 times k, again, where k is an integer. And the range, as always, for the cotangent function is going to go from negative infinity to positive Alright, let's move on to the next page in our notes. Seems like we have 2 more to go. Which is now in the secant function. Alright, secant function. Secant function is defined as 1 divided by the cosine of x. And the secant is undefined, or it has vertical asymptotes. Therefore, whenever the cosine is equal to 0, right? Because we can't divide by 0. So, where does the cosine of x be equal to 0? Well, we already took a look at that before, and we know that it's going to happen when this right here is true. So 2n plus 1 divided by 2 times pi, again, where n is an integer. So therefore, where do we have vertical asymptotes? We have vertical asymptotes. This might look a little bit familiar because this is something that we already talked about previously. So it's going to be at pi divided by 2, or negative pi divided by 2, 3 pi divided by 2, or negative 3 pi divided by 2, and we could just keep on going on and on and on. What is the principal cycle for secant? So I keep just telling you guys what this is, but let me refer back to in the notes so we're all on the same page where I'm getting this stuff from. Here, right here, this is our principal cycle. We're looking to find the principal cycle for the secant. And the secant, what we're going to have then is we're going to go between negative pi divided by 2 and pi divided by 2. And we're going to plop in here anything that we have in our bx plus c term. So, therefore, here our principal cycle is going to be from negative pi divided by 2 to pi divided by 2. Our period is given to us by p, and now if we look back at the secant, the period for the secant is now 2 pi divided by the absolute value of b. So we have 2 pi divided by the absolute value of b. Here, b is just equal to 1, so our period here is going to be equal to 2 pi. Our domain then is going to be all x values that are not equal to whenever we have vertical asymptotes. So here what we're going to then have is we're going to have pi divided by 2 plus our period times k, where k is an integer. Alright, so it also asks us to graph the secant. If we look at the graph of the secant, it's going to help us out with the range a little bit. For the graph of the secant, again, we're going to have vertical asymptotes at pi divided by 2 and negative pi divided by 2. And then we're going to have at 3 pi divided by 2 and negative 3 pi divided by 2. Get rid of this and right here. It's kind of getting in my way. Here we're going to call this value right here 1, and we're going to call this one right here negative 1. So that the graph of the secant looks something like this. And then it just repeats itself. And so on and so forth. Alright. So, our principal cycle then is in between these two vertical asymptotes right here. But what we're answering is our range, and as we can see here, our range is going to go, and let's take a look at this definitions page here one more time just to make sure we're all on the same page with this. we're going to go from negative infinity, and then our upper limit is going to be positive infinity, which makes sense, right? Here we can just keep on going up and up and up, and here we can keep on going down and down and down. So it makes sense that here we're going to go from negative infinity, and then our upper is going to also be positive infinity. But the important thing right here is this. We have this gap that's in between here. Now, in this problem, it's easy to see that our gap is going to go from negative 1 to 1. So we could just say that this is going to go to negative 1. And then this one right here is going to go from 1 to positive infinity. And these are included. And we could have the union right here. But the thing that I wanted to point out here on this definitions page is this. Whenever we're finding the range of this, again, we're going to go down to negative infinity and go up to positive infinity. But this right here, this is d minus the absolute value of a. And here we have d plus the absolute value of a. So here, d, again, if we have f of x is equal to a times the secant of bx plus or minus c plus or minus d, a is 1 and d is 0. And if you plug a as 1 and d as 0 into this, you're going to get 0 minus 1, which is negative 1. And we're going to get 0 plus 1, which is just 1, as the upper bound of this and the lower bound of this one. Right. So keep in mind here that this right here, and I'll write it up here so we have it for future examples, even though we could just refer back to it on that definitions page. This right here is going to be negative infinity up to d minus the absolute value of a, close parentheses, union with, close brackets, square brackets, open the square brackets for d plus the absolute value of a all the way up to positive infinity. All right. Again, this would be a good time for you to pause the video and give number 8 a chance by yourself. The thing to keep in mind here for 8 is that we always want b to be strictly greater than 0 whenever we're dealing with the principal cycle. So let's try to identify a, b, c, and d for number 8. And if we just go down the row, we would say that a is equal to 2, but now we would say that b is equal to negative 1, but we want b to be positive. So let's think about this. The secant is an even function. If it's an even function, then we can plug in the negative value into the secant function, and it would give us a result that would be the same as if we would plug in that positive of that value into the secant function. Another way of saying that is we can factor out a negative 1, get rid of that negative 1, and then whatever we're left with is going to give us the exact same result as it was before. So therefore here what we can say is that b is going to be equal to, well, let's do it. Y is equal to 2 times the secant of it, secant of, if I pull out a negative 1 out of this, this just becomes x. If I pull a negative 1 out of this, it becomes minus pi divided by 10. So these two now are equivalent. So now if I asked you what a is equal to, you would still tell me that it's negative, that it's positive 2. But now if I asked you what is b equal to, now you would tell me that it's a positive 1. C is the term that we're adding to the term with the x. So here we're adding a negative pi divided by 10 to it. And d is whatever we're adding or subtracting to all of this, so therefore d is going to be equal to 0. Alright, for our principal cycle then, what we want to do is we want to take negative pi divided by 2 and positive pi divided by 2. And we want to put in between these two inequalities whatever we have, whatever we're plugging into our trig function. Alright, so we have this. Now what we want to do is we want to solve for x. So let's go ahead and do the algebra on this one. If we want to solve for x, we're going to add a pi divided by 10 to all of this stuff. So what we want to first do is we want to get common denominators, and if we want to have down here in our denominator a 10, that means we're multiplying 5 to that. So then therefore this becomes negative 5 pi over 10. Here we'll still have everything in between here that we had before, and now this would then become 5 pi over 10. Now that we have a common denominator, we can add a pi divided by 10 to everything. So then this is going to become negative 4 pi divided by 10 is equal to x, which is strictly less than 6 pi divided by 10. Oh, how did that become an equal sign? That's not an equal sign. There should still be a strict inequality right here. We can simplify this. So what we could say is that this is the same thing as negative 2 pi over 5 is strictly less than x, which is strictly less than 3 pi over 5, which means that our principal cycle is going from negative 2 pi over 5 to 3 pi over 5. Our period is then given to us by 2 pi over the absolute value of b. The absolute value of b here is just 1, so here our period is equal to 2 pi. The phase shift is given to us by negative c divided by b. So it's going to become negative c is equal to negative pi over 10, and b is still just equal to 1. So then therefore this is just going to become pi over 10. Our domain is going to be all x values that are not equal to. We can start again off. Oh, I'm running off screen here a little bit. Sorry about that. So here all I took is that this right here became the upper limit. This right here became the lower limit, just like we did before for our principal cycle. For the domain now, we can use this 3 pi over 5 plus the period, which here the period, it's going to be half of the period for the secant. So let's see here. So here our period, let me make sure, for the domain for the secant, we have half of our period times k, and our period is equal to 2 pi, so half of the period is just going to be 2 pi divided by 2, or simply just pi, and this is times k again, where k is an integer. Let me backtrack right here and make sure that I got this right before 2. We had, this was pi divided by 2 plus our period. So this right here, I got it wrong up here. For the secant, it's half of our period. And if our period is 2 pi, then we should have 2 pi divided by 2, right? If you look right here for the secant, it's not the entire period, it's half of the period times k. Alright, so I had that small mistake up here before, glad that I caught it. Lastly then, our range for this is where we're going to use this portion up here. Now, our range is going to go from negative infinity to d minus the absolute value of a. So d, which is 0, minus the absolute value of 2, which is negative 2. So that's the square brackets. And then d plus the absolute value of a. So d plus the absolute value of a. So that's going to be then 2 all the way up to positive infinity. Alright, so that's number 8. Let's go on to number 9. And let's do what we were doing before for this. We're going to identify what A is equal to, what B is equal to, what C is equal to, and what D is equal to. Well, A is equal to negative 3. B is equal to 2, and it's positive, so we get to leave it this time. C is equal to pi over 8, and D is equal to 0. Our principal cycle is going to go from negative pi divided by 2 to pi divided by 2. And we're going to put everything in here that is inside these round parentheses. So therefore, this is going to be 2x plus pi divided by 8. Right. So now what we want to do is we want to solve for x. And we did the arithmetic on the last one, so let's go ahead and do the arithmetic on this one then too. First thing is that we want to do is we want to add pi divided by 8 to everything. An easy way to do that is just to get common denominators. So this is going to become 4 pi over 8 is strictly less than 2x plus pi over 8 strictly less than 4 pi over 8. So now we have common denominators, so now we can add pi divided by 8 to everything. It's going to become negative 3 pi over 8 is strictly less than 2x, which is strictly less than 5 pi over 8. And now we're going to divide everything by 2. So if we divide everything by 2, it's the same thing as multiplying it by 1/2. So then this is going to become negative 3 pi over 16 is strictly less than x, which is strictly less than 5 pi over 16. So that means that our principal cycle is going to go from negative 3 pi over 16 to 5 pi over 16. Right, for the period is again given to us by P is equal to 2 pi divided by the absolute value of B. B here is equal to 2, so it's going to become 2 pi divided by 2, which is simply just equal to pi. The phase shift is negative C divided by B. Negative C is going to be pi over 8. We determined that C from before is pi divided by 8, so it's going to become pi over 8 divided by B, and B is equal to 2. So therefore this is going to become negative pi over 16. Our domain is going to be all x values that are not equal to. We can start off with the upper limit of our principal cycle, which is 5 pi over 16. And now we're going to add to it 1/2 of our period, and our period is equal to pi. And then we're going to multiply this to k, where again k is an integer. And lastly, our range, we're going to go from negative infinity to d minus the absolute value of a. So d minus the absolute value of a. So it's going to become 0 minus 3. and then we're going to go union that with d plus the absolute value of 3, so 0 plus the absolute value of negative 3, and the absolute value of negative 3 is 3, so then this is going to be 3 to positive infinity. Alright, and that's this page of the notes. We have one more page of notes to do for this section, and that's for the cosecant. And for the cosecant, we're going to do a lot of stuff that's similar to what we did for the previous trig functions. For the cosecant now, we have that the cosecant is defined as 1 divided by the sine. So whenever the sine is equal to 0, that's when we're going to have vertical asymptotes. And we know that sine is going to be equal to 0 for n times pi, where n is an integer. So we've looked at that before, and therefore we're going to have vertical asymptotes at 0, and then we're going to go multiples of pi both above and multiples of pi below 0. Right? Dot, dot, dot. For the, so for number 10, for the principal cycle of the cosecant, the principal cycle for the cosecant is going to go from 0 to pi. So therefore, for the principal cycle of the cosecant, we're going to have that this goes from 0 to pi. The period for the cosecant is given to us by 2 pi divided by the absolute value of b. Here the absolute value of b is again just 1, so we just have that it's 2 pi. The domain is going to be all x values that are not equal to whenever we have vertical asymptotes, so that's going to be for n times pi, since that's where we have vertical asymptotes. And our range is going to again be best if we look at the graph of this. So here we're going to have vertical asymptotes at each pi. So here this is pi, this is 2 pi, this is negative pi, this is negative 2 pi. So the way that the cosecant graph looks is it looks, and then here this is positive 1, this is negative 1, looks something like this. And then it repeats itself. Right, and so on and so forth. This right here, this is our principal cycle. Right, from 0 to pi. But what we're working on now is the range. As we can see, we're going to go all the way up to positive infinity and all the way down to negative infinity. So therefore, our range is going to go down to negative infinity, and we're going to go all the way up to positive infinity. However, we never touch in between here, right? Never go in between here and in between here. So in the graph for this one, it's relatively easy that we're going to go from negative infinity to negative 1. We're going to union that with 1 to positive infinity. But again, keep in mind that what we're basically doing here is that d minus the absolute value of a, and here it's again d plus the absolute value of a. Alright, just like I said on the previous problems, now would be a great spot for you to pause the video and to give number 11 a shot by yourself. Again, what we're going to try to do is we're going to try to identify A, B, C, and D. And I'm hoping that that's becoming a little bit easier for everybody. A is going to be equal to negative 3. B is whatever we're multiplying the x term by. Here it's 1/4. C is going to be equal to 0. And now D, we have a 1 right here. Right? D is then therefore going to be equal to 1. For our principal cycle, we're going to have 0 and pi, and in between here we're going to have whatever we have inside the parentheses, or the bx plus or minus c term, which is just going to be x over 4. So therefore, here our principal cycle is going to go from 0, right, since we're solving for x, to 4 pi. We want to write that in interval notation. We can also write it like this. Our period for the cosecant function is given to us by 2 pi over the absolute value of b. And just to make sure that we're all on the same page with where we're getting that from again, cosecant has a period of 2 pi divided by the absolute value of b. Here, therefore, we're going to have 2 pi. The absolute value of b is 1/4. So then, therefore, this is going to come out to 8 pi. The phase shift is given to us by negative c over b. Therefore, we're going to have negative c is equal to 0 divided by b, which is 1/4. Well, 0 divided by anything is always just going to be equal to 0, so we have 0 for our phase shift. Our domain is going to be all x values that are not equal to. So let's take a look at this here. Again, to make sure that we're all on the same page with this, for the cosecant function, we're going to have an asymptote, and we're going to add 1/2 of the period to it. 1/2 of the period to it, times multiples, or times an integer. So we can start off with this 4 pi, or we really could start just as easily off with this 0. It really doesn't matter. So just for simplicity, I'll say that it's 0 plus 1/2 of the period, and the period here we said was equal to 8 pi times k, again, where k is an integer. And yes, we absolutely could simplify this. We could just call this 4 pi k if we wanted to. The range, again, the range is given to us from negative infinity to d minus the absolute value of a, square brackets, and then union with d plus the absolute value of a, all the way up to positive infinity. So therefore here we're going to go from negative infinity, d is equal to 1 minus the absolute value of a, which is the absolute value of 3. So we're going to have 1 minus 3, which is simply just equal to -2. And then here we're going to have 1 plus the absolute value of a. So we're going to have 1 plus 3, which is equal to 4, and take that all the way up to positive infinity. Right. So now for number 12, and also the last problem in this section. This was a rather long section. We're going to still tackle this just the same way we've been tackling them all. We're going to identify what A is equal to, what B is equal to, what C is equal to, and what D is equal to. So here we have that A is equal to 1, and B, we would say that B is equal to -2. But here, we want to make sure that B is always strictly greater than 0. So therefore, that B being equal to -2 is no good. So let's take a look at this. The cosecant function is an odd function. The cosecant function is an odd function. So that means that what we can do is we can pull this negative out front, pull a -1 out of -2x, just leaves us with 2x. Pull a -1 out of pi over 4, it's going to leave us with -pi over 4. And now here we still have a -2. So now these two are equivalent, right? We pulled out the negative out of this, so we put the negative out here. That does not affect this negative 2 at the end. Now if we go through the exact same questions about what is A equal to, now you would say that A is equal to negative 1. But now B is equal to a positive 2, which is exactly what we want. C is equal to negative pi over 4, and D is equal to negative 2. So therefore, for our principal cycle, we're going to go from 0, strictly less than whatever we have right here, the bx plus or minus c term, which now is equal to 2x minus pi over 4. And that's going to be strictly less than pi. Alright, let's solve for x. We want to have, well, here it's relatively easy. Here, if we add pi over 4 to everything, we're going to have pi over 4 is strictly less than 2x, which is strictly less than. Here, if we have pi and add a quarter of a pi to it, we have 5 pi over 4. And now we're going to divide everything by 2, which is just the same thing as multiplying everything by a half. And that gives us this. So therefore, our principal cycle is going to go from pi over 8 to 5 pi over 8. Our period is still given to us by P is equal to 2 pi over the absolute value of B. Here we have 2 pi and B is 2, so therefore our period is just equal to pi. Our phase shift is given to us by negative c divided by b. So we have negative c is equal to negative pi over 4, and b is equal to 2, which means that this is going to result in pi over 8. The domain is given to us by all x values that are not equal to. Again, we can use either one of these that we want. I'm going to start off with the pi over 8, which is one of our vertical asymptotes. And to that, we want to add 1/2 of our period, which is equal to pi times k. As always, where k is an integer. Now, last but not least is our range, and our range is always going to go from negative infinity all the way up to positive infinity. We're going to union these two things, and here we're going to have d minus the absolute value of a, so negative 2 minus the absolute value of negative 1, or 2 minus 1, negative 2 minus 1 becomes negative 3. Here we're going to have d plus the absolute value of a, which becomes negative 2 plus negative 1. So then this is going to become negative 1. And there is our range. So I hope that these examples that we finish off this section with for each one of these trig functions, I'm hoping that that helped out clarify some of these definitions. The next couple of problems are the practice problems, but as always, those are left for you. So that concludes the video for section 6.3.